Hello everyone, my name is Jia Zhe, and along with me are my group mates Nathan and Jingwei. And today we'll be presenting on our project Only Pets, Predicting Popularity Score. Here's our project overview, the problem statement. So we notice an increasing number of unadopted pets at shelters, and potential adopters are either at shelters in person or picking from pets from a collage of photos. And because of this, the first impressions usually come from the photos themselves. And therefore, photographs of pets are highly valuable for adoption agencies and shelters. And our aim is to optimize photos of these pets, increasing attraction of the pet in the photo, and hopefully increasing adoption rate of these pets. We first conducted an exploratory data analysis. Here we have a frequency graph of popularity score. The distribution of popularity score is right skewed, and the majority of the scores are concentrated between 20 and 60. This distribution has a skewness of 1.17 and a kurtosis of 1.38. Because of this skewness, popularity score may benefit from a transformation to reduce skewness during modeling. We also plotted a correlation matrix between the features as well as a distribution count of each features. Although we found some correlation between certain features, but overall, we also found that the individual metadata features have weak correlation with popularity score itself. Therefore, we chose not to include them in our modeling. Next is our data pre-processing. The popularity scores in the original dataset range from 0 to 100. We normalize these scores to the range of 0 to 1 by dividing each score by 100. This stabilizes the training process and ensures consistent output ranges. And this also improves the gradient flow during backpropagation. We also use stratified K-fold, and this method ensures that each fold has a similar distribution of popularity scores, mitigating the risk of overfitting to specific data subsets. We created a training and validation pipeline for data augmentation. The training pipeline included resizing and cropping, horizontal and vertical flips, geometric transformations, and brightness augmentations. The goal is for the data to be generalized and for the model to be picked up more features. As for validation pipeline, we also did a resizing of the images. Both training and validation pipelines apply consistent normalization using ImageNet statistics, where the mean and standard deviation are the RGB channels. This aligns the input with the pre-trained model's expectations. So here is the model that we chose, which is the shifted window transformer or SWIN transformer. The SWIN transformer is a vision transformer that introduces hierarchical feature representation and efficient self-attention mechanisms, making it highly suitable for image-based tasks. It was originally designed for image classification. So from the example, the input image is divided into non-overlapping windows, and self-attention is applied within each window. In subsequent layers, the windows are shifted, allowing the model to capture cross-window dependencies. This strategy reduces computational complexity compared to traditional transformers, while maintaining the ability to model long-range interactions. For example, on the left, we have the model hierarchical architecture, and on the right are the two successive SWIN transformer blocks. We also have an example of an image and the windows at layer L that will be passed into the block, and the output will be layer L+1 with the windows shifted. This shows how the SWIN transformer processes the input at multiple scales, enabling it to extract both local fine-grained and global coarse-grained features. This hierarchical structure is particularly advantageous for images, as it allows the models to focus on both detailed features like pet facial expressions and broader contextual cues like image composition for our task. As mentioned earlier, model was originally designed for classification tasks, and to fit our regression tasks, we modified the output structure to give a singular scalar value representing the normalized popularity score. Firstly, through the use of a global average pooling layer, this reduces spatial dimensions of feature maps into a single vector, and so ensures most important features from spatial dimensions are preserved. Suitable tasks for global context is critical. Secondly, a fully connected layer. The single vector is passed into this fully connected layer, mapping condensed feature vector into a single scalar value, which in this case is our popularity score. So for our model parameters, we use a smooth L1 loss as the loss function. This loss function combines the advantages of L1 and L2 loss functions, balancing robustness to outliers with sensitivity to small errors. The model is also less sensitive to large deviations in predictions, which is particularly useful for noisy datasets, like the popularity dataset. As for our optimizers, we tested with 3 different optimizers: normal Adam, Adam with weight decay, and stochastic gradient descent. We found out that Adam with weight decay consistently achieved lower RMSE compared to Adam and SGD. Its ability to handle large weight updates and regularization properties make it the optimal choice. Here are the other training strategies we implemented. Firstly, gradient clipping was used with a maximum norm threshold set to 1. This prevents the gradient explosion problem where the gradient gets too large, at the same time leaving smaller gradients unaffected. We also maintain an exponential moving average of the model weights throughout training, updating at each step according to the formula on the right. Alpha was set to 0.99 for optimal temporal smoothing. The EMA weights are used for validation and inference, providing more stable and reliable predictions by averaging out high-frequency variations in the model parameters. We also implemented cosine annealing with warm restarts, which allows us to dynamically change our learning rate through a scheduler. This scheduler progressively reduces the learning rate following a cosine curve and periodically resetting it, enabling the model to escape local minima while maintaining steady convergence. The warm restart mechanism provides additional opportunities for the model to explore different regions of the loss landscape, particularly beneficial for our complex regression tasks. So here are our results. Initially, we used a normal CNN model without strategies and data augmentation mentioned earlier. And after fully implementing the new strategies, augmentations, and new model, we observe an improvement to our results. Here are our key findings. Firstly, the comprehensive augmentation pipeline proved crucial for model generalization with the full augmentation strategy, reducing RMSE by 0.3 points compared to baseline augmentations. Particularly effective was geometric transformations, which helped the model to adapt to various pet photography conditions. Our new proposed model also improved our accuracy. The swing transformer was able to pick up more salient attention windows as compared to our original CNN model, and this allowed for better prediction of popularity score. The combination of Adam with weight decay, optimizer, and cosine annealing warm restarts provides stable training dynamics. The decoupled weight decay in Adam prevented overfitting, while the warm restarts help escape local minima, contributing to consistent performance across all folds. Finally, the implementation of EMA significantly enhanced prediction stability, particularly for edge cases with extreme popularity scores. The improvement in RMSE demonstrates the effectiveness of weight averaging in reducing prediction variance. So for some closing remarks, although our proposed method has improved overall RMSE score, our final result was still not as high as compared to other competitors in the competition. We believe that what we have done sets a solid foundation for future development, and this could include exploration of ensemble techniques, combining different model architectures or alternative loss functions for faster inference.
Thank you for listening to our presentation.